Okay, we just recorded it by this time recording it. Okay, so if anybody is missing it, you can listen at your home whenever you want. So I will tell you a little bit about the Center of Science Information that has many universities, including MIT, Princeton, Stanford, Berkeley, San Diego, even Hawaii. So from East Coast to West Coast. And I want to tell you why this center started. So the center is part of something what is called STC, Science and Technology Center. It was created in 2010 for 5 years, that extended for another 5 years. It was 50 million investment. And our goal was to understand actually what is information. And that's what I want to start. So the motivation is quite simple. Shannon, the great man of information theory, when he started it, he focused on data transmission compression. That was his focus. The definition of entropy, he did not introduce entropy, but he used entropy and mutual information to define information. I will try to explain to you that we have to go beyond that. And entropy is not really information. And I want you, I think we have only man on this, so I want that you actually can explain information to a man on the street. So simple, understandable definition of information. So first, why we have to go beyond data transmission and compression? Because nowadays, as you know very well, information is not only transmitted, it has to be secure, it has to be curated, organized, represented, analyzed, inferred. In data science, you have to learn how much information is there. So there are many, many different usages of information beyond the original goal of Shannon. Because of this, we put a pretty high threshold of what we actually want to accomplish. And we wanted to advance science and technology through a new quantitative understanding of the representation, communication, and processing of information in many different systems, biological, physical, social, and engineering. This was the goal. However, it was too broad. So first of all, there is no doubt that information biology is the key for understanding how living organs are working. And these are not my words. These are words of a Nobel Prize winner, North. I will show you in a second. The cells do communicate, and to understand how information is transferred between cells is the key to understand, actually, to build a theory of biology. In economy, information is everything. If you have information, you can make money, or you can make others to pay for it. Unfortunately, one of the key components of information economy is when biology is time. And Shannon did not, and then information theorists did not make much progress in this respect. So one of our goals was to understand technical information. Then you have data science when structural information is the key. You want to know how much information in the graph or in organization. And actually, most of the chemistry is in the structure of let's say, DNA and so on. So you need to understand the structural information. Finally, physics, actually in 1928, if I remember, Szilard showed us that energy and information are related. One bit of information is equivalent to something like KT log 2, I don't remember, energy. And this was interesting. And you can actually, there are interesting work between physics and information. We won't go there. what the center focus and what we focus today is structural and temporal information, semantics and other things. In dynamic and information, in the dynamic environment, when Shannon started, it was point-to-point communication, beautiful mathematics was done, but we are living in interconnected worlds and we need to understand dynamic information. The next thing is limited resources. So to explain this, imagine that, and this is, by the way, when you have your cell and your energy, your battery is dying, so you can see how much you can learn. Or when there is a cell with limited energy, and this cell has to recover or transmit information within limited resources. A simple example that I give it is usually the following. Let's say I'm sending to you a big, huge number with, let's say, 100 digits, but you have resources to store only one digit. Definitely, you cannot learn what the number is, but you can learn something. So the question is how much you can learn with limited resources. I'm doing some work with IBM right now, and that this actually comes out when you want to find a summary of a, let's say, first order logic document that is the most informative, whatever it means, and we don't know yet what it means. So this is another example. Let me also pick up representational invariant information. What do I mean by this? Okay, we are speaking English now, but you might, in 5 seconds, we might speak Polish. We might say, or let's say you have one-to-one translation. What I speak in English to Polish, one-to-one translation. I think we all agree that these two representations, English and Polish, have the same information. But if you apply any statistical representation of information, entropy, whatever you want, you will get completely different numbers. And you know why? Because we have a lot of shit there in Polish, when in English there is something else. So something is interesting. The same meaning, the same information, if it represents in different languages of the different representation, it will have a different information. Can we find a unique representation on, I call it invariant information? We didn't make much progress on this. So what I will talk today will be structural and temporal, and mostly in graphs. But before we go there, let's philosophize a little more, okay? So let's focus on data science, and we claim that the paradigm triad that everybody has to deal with in data science is from data to information to knowledge. And information is at the heart of this triad. Knowledge is very complicated to define. I'm not going to do it. Let me define it in a very simple way. Let's say that it is information and action. So whatever this second part of this triad give it to you, whatever you learn from your data, you have to interpret, whether it is, let's say, a doctor or a lawyer, whatever. I'm not going to deal with knowledge. It's too complicated. Data, everybody understands. So let's focus on information. What is information? And I will try to argue that information is a measure of distinguishability. If you cannot distinguish, you do not have information. And Shannon did this because he wanted to distinguish signal from noise in telecommunication. But it's more than this. So we are trying to frame the foundation. So let's go to information. I spent a lot of time thinking about it. And actually, in 1938, if I remember, Wojciech wrote an article in German, actually, and he was saying, information is only that which produces information. It relates to relativity of information, depends who is the recipient of this information. And let's say read the second, information is only that which is understood. Now, these two things, Feynman, and he was always excellent in explaining things in simple language. He said information is as much a property of your own knowledge as anything is a message. Just to give you a simple example, if you submitted a paper to a conference, let's say called, we still don't know the results, and in a month you get an email. There will be a long email, but the first 3 letters, 3 words tells you everything. I'm pleased or I regret. And you don't need to read anything else, you know what it is, okay? Because you have this prior knowledge. Finally, information is not absolute. Now, if you take a piece, okay, look at this slide. How much this slide that you see in front of you, how much information is there? You cannot answer until I tell you a little bit, because some of you might count the number of characters, do the histogram, that log of this, and get some kind of entropy. But the others might count the number of words, and you'll have different information. And finally, somebody decided, I want to look at the shape of the letters. Again, you will get some information about something else. So information is not absolute. It depends on the context. Okay, let's go to Peter Nars. And I told you that in 2008, he wrote a beautiful 4 pages article in Nature, arguing that biology has to focus on information, otherwise not much progress will be done. He said, focus on information flow, which help to understand better the generalization of spatial and temporal order in cells. So information flow is the key. Some people are trying to do it, but I think on too detailed level, however, without detail, nothing you can do. So this is one thing. And finally, the thing that we are gonna focus today is the challenge that was introduced by Frederick Brook in 2003, if I remember, at JCM. He wrote a 3-4 page letter, 50 years, 3 challenges of 50 years old computer science. Just a small digression, just about computer science. As you know, I am at Purdue. Purdue was the first university having the department of computer science in 1962. It was 6 months, if I remember, before Stanford. So going back to Brooks, he's saying that one of the biggest challenge of 50 years computer science, it was 2003, whatever, is to understand information and embedding in structures. Whether it's graph, organization, or something else, that's what we'd like to do. Let's make a little bit progress on the last one, and we'll see what we can do. Okay, so by the way, if there is any question, you can chip in whenever you want. Maybe when I finish this introductory, I will ask if there is any question. So to continue, information, at least what we see, has this flavor of relativity. A different recipient might interpret information different ways: rationality, prior knowledge, time, spatial context. With my colleague from Politechnika Gdańska, Professor Konorski, once we start thinking about it, and we come up with a definition that is too general, but basically a piece of data carries information if it can impact a recipient ability to achieve the objective of some activity within a given context. As you see, it's philosophy, not engineering. So let me focus on more on engineering and argue that information is the measure of distinguishability. So you have to define, it depends, of course, how you define distinguishability. Noise, signal. You want to distinguish some patterns in a huge database, or a cell must to distinguish through timing some events, but it has to be distinguished. Now, you might say that this is BS, there is nothing new. So let's see what other people say. Charles Bennett, he is in IBM still. He's a Shannon winner 2,000 years ago, 2 years ago. He worked in quantum and crypto quantum, a great guy. Hear what he say, and I find this quote after we came up with this understanding of information distinguishability. So he says, so information is really a very useful abstraction. It is a notion of distinguishability abstracted away from what we are distinguishing or from the carrier of information. So I'm pretty sure that we're on the right track. So once you distinguish something, you can actually define information one way or another. Kolmogorov actually was saying something very strong, because most of the people in information theory tells you that information is probability. But Kolmogorov says information theory must precede probability theory and not based on it. But the very essence of the discipline, foundational information theory, have a finite combinatorial character, and that's what I want to underline. So there are, in a sense, we can think of three different ways of looking at information. First, knowledge and logic. That is more for philosopher, but not only. I will come to this in a second, because the logic is a very important part of information. The information type B, where it's counting distinction, that's what we are talking. But you see, logic is important, because if you have some logical constraints, let's say in the first order logic, it restricts what you can count and you can distinguish. So logic, that's what we tried to do for the last 2 years, and we didn't succeed. We wanted to do a workshop in Krakow that we call computation, logic, and information, combining all of these aspects. Computation, because I told you limited resources, have a directly impact of what you can learn. And there is also Kolmogorov algorithmic complexity. We are focusing on B, and we're throwing away logic for now. It's too complicated. So that's what we have. Okay, before I finish this introductory part, so let's go to this triad: data, information, and actionable insight or knowledge. We claim that this is the way to look at data science. And the heart of this is what you can learn, how much learnable information your data has. Remember, in this case, noise is not thermal noise that's in communication, but noise is actually the other data that obfuscate what you can learn. And because of this, we have to understand how much learnable information is in the data set that you want to deal with. Once you know it, and then the theory, so you are a theoretician, so how you define learnable information. Once I know it, we can design algorithms that achieve, at least asymptotically, this learnable information. And we know that you can't do more than this. So this is like a lower bound. In compression, this lower bound was entropy. We know that you cannot compress more than to the entropy. Of course, there are special cases, but they are very small probability, and you want to ignore it. So I call it information efficient computation, when you want to learn most of learnable information and not more, and not focusing of very rare event. Lempel-Ziv compression is the best example. It doesn't, I can create a file that Lempel-Ziv compress terribly, actually can introduce, can increase the size, but it happens very rarely. So you want to focus what is typical, what actually, and you define learnable information in some sense in a statistical sense. So let me see. Okay, so if you want to learn about a little bit of this philosophical stuff that I'm talking today, I refer to a paper that I wrote with my colleague, Anand Grama, Frontiers of Science and Information, from Shannon to Turing. and it was published in January 2018. If I had a chance to write it again, I would say from Shannon to Gödel to Turing, because the logic plays a very important role, but not for now. Okay, any question before I go to the next one? And this will be more mathematical, more algorithmic.
I have a question.
Go ahead.
So I'm not sure if I understood the previous slide correctly. So in Shannon theory, the pure noise has a lot of information because it has high entropy, right?
Go ahead.
But in our theory, it has little information because we cannot learn anything from the noise, right?
Not really. Let me try to see how can I explain. I would say this way. Noise means different things in different systems. In telecommunication, noise, yes, obstructs the information. So when you transmit, it can change some zeros to ones. And you want to see with a given level of noise or power of noise, how much reliable information you can learn with high probability, by the way, nothing for sure. So here noise is different than I would say the noise that is in huge database where the noise is coming from the fact that records are too close to each other, you cannot distinguish it. So for me, noise and distinguishability are important, except that noise has to be interpreted differently in different environment. That's what I would say.
Okay, thank you.
Anybody else? Okay, so let's go to examples of this high level talk or philosophy, the high threshold that I put in front of us, trying to understand structural and temporal information. And always when you are dealing with real stuff, you have to go down and try to find good, simple example, but then Einstein says simple yet, but not simpler than that. So something that is non-trivial. And we do it with dynamic networks. And there are many dynamic networks. Brain network that was developed over evolution, over millions of years, is something that we would like to understand. So why this network is a functional network of different functions. So for example, when I do walk, I have to breathe, but I don't have to think or dance or anything like this. So there is a clear correlation between walking and breathing, but not on the other. There are functions in the brain that seems to be correlated, and using MRI, we can actually create a correlation between different functions. And here's the problem. I got an MRI of a healthy brain, just got, let's say, a month ago, or I have a snapshot of a dynamic network because functions do add and are deleted over evolution. I see what I see now, and from that structure, I would like to do inverse engineering and try to ask the question, which function was early in evolution, which part of the brain was developed earlier than the others? So in a sense, I'm trying to understand the arrival of nodes in a dynamic network. I will explain that more later, and I will formulate this mathematically. This is another dynamic network, protein-protein network, where different proteins are related and they are correlated with other proteins through some enzyme and so on and so on. So there's this protein-protein interaction network. It, over evolution, also this network changed. And what we see right now is a snapshot. And I would like to know which of these proteins are the oldest, because what I understand, ancient proteins have some impact on, let's say, cancer. So we would like to know it. Now, let me observe that the protein-protein network topology, if you can see, is completely different, looks different than brain network. It is clear to us that protein-protein network is generating by a different model than brain network. So I will define today preferential attachment model and duplication model. And actually, Abram and Krzysztof is on the talk. So one of them study a lot about preferential attachment, and we mostly discuss preferential attachment. When Dr. Turowski will talk in about 2-3 weeks, he will tell you more about another model that is related more to the protein-protein, which I define in a second. So there are other artificially created interaction network, internet on Facebook. Unfortunately, you spend too much time on this nonsense, but still we can study it. And in the Facebook, you can actually try to trace friends or group of friends or something like this. Okay, let's go to, okay, first another motivation, what I will tell you in a second. And that is actually occurring very much because it's related to viruses. So imagine there is a small town, let's say West Lafayette, where I do live, and a virus arrives and infects the whole town. So what people do, people go to a hospital, and people in hospital trying to connect who infected whom. So you have a structure like this, but the structure is not exactly in the order that the infection happened. From this structure that you see right now, our job is actually either to find how this network was created, so which node, where it started, and so on, or you might have a basically graph on which you infect one node and you see how infection happened. And I think Dr. Abram will tell you about something like this in 2 weeks. So that is the job. Here's another, okay, so there are plenty of possible applications on spam, spread of infection disease, financial transaction, you want to know who is trading money with whom, and biological infection, okay? And here's what I will tell you in detail later, but this is an example that will focus. I have some data, let's say from MRI, from a healthy brain, and using correlation between different parts of the brain, I create a node. Let me see, I should be able actually to get, let me see. Okay. Let's see. No. Oh, okay. Just a second. Let me try to see if I can get it. Okay. Now, even I can learn. Okay. So this is a graph that we created from this data. This is a snapshot of the connection between different parts of the brain. Based on this structure, can I infer how evolution evolved? So can I say that this part is older than this part and so on and so on? So this is the question, but we have to first formulate it mathematically. And this was Abraham, Dr. Magner, who actually gave us perfect definition. Here is a graph that I'm gonna deal with this. It is called preferential attachment graph. Every node that arrives connects to 3 nodes, as you can see, but it connects more likely to nodes with higher degree than lower degree. That's how it is called preferential attachment. I'll give you a definition in a second. But you can see how it is defined. So this is the graph. Now, what I actually see is not this graph. I see the structure, but the nodes, I don't know that this node was number 1. I just number it randomly because I only see the structure. That's what I can see. I don't know what the labels are. So let's say we formulate this way. You have a preferential attachment graph or any other graph with labels that are exactly the time of the node arrival. So this is number 1 arrival, number 2, and so on. But there is an evil who just permutes all of this, and that's what I see. So this is a permuted graph. So this is now number 3, and number 1 is somewhere here. But my job is, based on the structure is preserved. Can I infer the original levels, which is the inverse engineering, yes? Which node arrive first? I do not have deletion. So mathematically speaking, what we want to find an inverse permutation that recovers the original levels. That is actually a daunting task, because I have to tell you for every 2 nodes, which node arrived before the other one. Since there are n choose 2 nodes, I have to correctly guess n choose 2 pairs, which is quite a lot, n squared. So what we can do, okay. I will tell you a little bit what we can do. Let's focus on 3 different graphs, but mostly I will talk about one. Erdo-Chenier, everybody knows. So I remind you what is Erdo-Chenier graph, GNP. I have n nodes. I pick up randomly 2 nodes, and I connect them with probability P or not with probability 1 minus P. It is not a dynamic graph, okay? But it's a good test bed. Preferential attachment P and M that I define to you is basically definition here. I start with node 1, I do something, and then at time t, when a new node arrives at time t, I connect it to the new node, I connect it to M existing nodes, but I connect them to connect to those nodes that have higher degree. So probability of connecting to node K depends on its degree. The idea is the older nodes should have higher degree. There is other model, duplication diversion model, which I now try to explain to you, okay? So this is a small dam. So I start with some initial graph. When a new node arrives, the first thing it chooses is one node. But I do connect to all his neighbors. So I connect to C, D, and F. And then I delete some of this connection with probability 1 minus P. But that's not it, because this will generate a lot of isolated nodes. Then this node 1 connects randomly to some of the existing nodes with small probability. This probability depends how many nodes already is there. So this is how I create. Let me choose node 2. Node 2 chooses I. Node I does not have any neighbors, so it connects to nothing. But in the second phase, a small probability, it connects to nodes, other nodes. So you see, it connects a little bit. Let's see node number 3. It could be, so it connects to A, delete something, and then to others. And I think you get the blue, the jazz. So here, how it's defined. So starting with some graph Gn0 and with 2 parameters P and R, I choose randomly one node U, and then I do 2 steps. In step A, I delete some of the connection of the neighbors of U with probability 1 minus P. And on the top of this, for nodes that are not neighbors of U, I connect to them with probability R over N, where N is the number of existing nodes and R are some parameters. Okay. Is it clear? Okay. There is one parameter of the graph that will play crucial role for us. And that is symmetry of a graph, an automorphism. And I'm sure you know it very well, but let me quickly remind you. So what is an automorphism? An automorphism is a form of symmetry, and it is mapped into itself so that edge connectivity is preserved. So Example, here the graph. When I permute B and C and D and E, I'm getting exactly the same graph, the same adjacency matrix. So I have one permutation except identity permutation. So this graph has automorphism of this graph consists of two permutations, and cardinality of this is 2. Okay, so this is one thing that is very important. I need to know what the cardinality of the automorphic groups, which will describe to me symmetry. Think about tree. In a tree, at the bottom, when you have two nodes on the same level, when I permute them, they see exactly the same topology. That's what permutation is, more or less. But there is another parameter, which is important. Some permutation might not be consistent with the model at which the graph is generated. So we won't define G of gamma of G, set of permutations such that it has positive probability. Example, imagine I'm doing right now another preferential attachment graph. Okay, so it's 3 nodes, 4. See, node number 4 connects to 1, 3, and 2. Node number 2 has 3 connections to number 1. Okay, let's permute this, and I permute 4 and 2. This permutation cannot be generated by the model that I just described to you, because we know the node number 4 is the last node, and it must have 3 connections, but it has 5. So this permutation is not permittable. Therefore, we define set of admissible graphs, all permutations that the model can generate. And of course, symmetry, I mean distinct permutation. So the size of this graph is the size of gamma, the permutation that are admissible, divided by automorphism, or size of automorphism, because when I permute within the automorphic group, I'm not changing, let's say, adjacency matrix. I'm not changing the graph. So this is admissible of this graph is the number of distinct permutation or distinct graphs, if you want to say. This is one parameter that's very important in our analysis. One more thing, I defined to you this preferential attachment graph. This the work was done with Dr. Magner when he was my PhD student, now postdoc, and now he is big professor. And that work that I will present here will be quite a lot from what we did together. Duplication diversion graph is something that when Dr. Turotsky was here, we work a lot, we understand it. It's actually much harder to analyze. And I will explain why. The reason that we are talking about this, because what works for preferential attachment graph doesn't work for duplication graph. And that's why it is interesting to know what's going on. Okay, so let's go back to the question that I asked you before. You remember the graph. I had a preferential attachment graph. Evil did come, permute the labels. I have the permuted graph, and I want to recover the original graph. So recover the original permutation, the inverse permutation. Can I do it? It turns out that the probability of recovering exactly this is close to 0. So because the number of incorrect graph edges that I recover is n squared, it can be proved. So basically, there is no way to recover with high probability the original arrivals of a dynamic graph in Erdős-Rényi preferential attachment. I'm pretty sure that's what we proved, but I'm pretty sure it was also for duplication network. So this is one example when it's good to analyze before you start doing something, knowing that you fail. So later in the talk, I will change a little bit the original permutation, original formulation, that is still interesting as a practical application when we will not insist that you have to recover exact permutation, but partial order is good for us. So basically, I will recover, let's say, some groups of nodes. And I would say that the group 1 definitely arrived before group 2, but I don't know what happened within the group. We will come back to this, because what I want to do right now is to talk about structural compression. Any question? Okay, today the talk will be a little longer, as I told you, but usually it should be, we should be done with 1 hour. Okay, so what we want to do, you have a label graph, and then I delete labels, and this is unlabeled graph. I call it LG, structural graph. I want to know how many bits I need to describe label graph and unlabeled graph. In a sense, unlabeled graph and structural entropy tells me a little bit about structure. So here what we will do, we have to define structural entropy. I can't write anything, but I think we will explain this. So I want to find, so we know that the lower bound for a graph compression and structural entropy, structure is some kind of entropy. The label graph entropy I denote by SG, structure entropy HSG. I want to know what is the relation between them. Okay, it's not that simple. It's not even that simple as written on this slide. So let me do it. So if within the admissible set, remember what is admissible set? It's basically those permutations that have a chance to be generated and are distinct, so it belongs to different, belongs to the same automorphic group. If within the automorphic group, within the admissible set, all admissible graphs, permutation within admissible set are equally likely, then the relationship between graph entropy, structural entropy is given here. When this is gamma, so this is permissible set, and this is automorphic. The reason is quite simple. So what's happened? How can I write graph entropy? Graph entropy I can write as a joint entropy of graph and structure, because a graph contains a structure. So H of G is the same as F of G comma S of G. Then I use a conditional entropy. So I write H of G is equal entropy of the graph plus conditional entropy of S and G. But this, because I assume that all of the permutation within the same admissible set are equally likely, is given this is exactly what it is. And then we know the entropy in this case is nothing else as log of this set. By the way, this set we know as a ratio of gamma and automorphism. So if I take the log, subtract, and take expectation, that's what I'm getting. So I have to understand. So usually it is easy to compute a graph entropy, much harder structural entropy. But I need to understand this to point to especially automorphism. There will be a lot of discussion now. How big is the automorphic group? And I will do it quickly for Erdos-Renyi and then focus a little bit on preferential attachment. Any question? Okay, so let me do Erdos-Renyi, but rather quickly. In the book, you have 30, 40 pages of proofs of this, which seems to be simple, but actually requires, especially if you want to be precise. So first of all, graph entropy, which I denote here as H of S, when P is not too small or not too large, is the first term is nothing else as the label graph entropy. Why? Imagine, okay, so how the graph is generated. I take n nodes, I choose a pair, any two nodes, so, and I can do it on n choose two ways. And then I connect them with probability P. This happens independently. So think of this as a matrix. When you put 0 and 1 independently, and how much entropy there is n choose 2 times the entropy of 1, you can say. So this is graph entropy. But the question is, and I go back, okay, for Diversion, this is easy. This is basically gamma is n factorial. Every permutation is feasible. So this is basically log n factorial. Now the question is how big is this one? It turns out that very small. There is a proof also in our book, but we didn't do it, that basically with high probability, randomly selected Diversion graph has automorphism equal, the cardinality equal 1. So it is asymmetric. So this is basically 0. Not completely, but close to 0. So you see, this is no n factorial of gamma, plus some additional terms coming from the fact that with some small probability, graph might be symmetric, I have to take into account. Okay, so this is the first part of this, what I call information efficient computation. I know my lower bound. I know my bottom line. I cannot compress more than this number. The second part, sometimes much harder, is how to find an algorithm that achieves this lower bound. Maybe the first two terms. So this is my next job. I want to find an algorithm, and I show you on the next slide, that basically I can prove, and the proof might be actually quite complicated, that the compression is n choose 2 HP minus n log n. Now, finding a graph, a compression that achieves the first term is trivial, because here what I will do. Again, imagine you have adjacency matrix where you randomly put 0 and 1s. Read this matrix that is symmetric. So you basically read n choose 2 line by line. You get a long string of length n choose 2. Apply Lempersiv on any other algorithm, you exactly get this one. But this term is actually quite big. So for example, if P is small, like log n over n, these two terms are almost the same. They differ by log. So we need a better algorithm. Before I come back to this, let me describe very briefly, I don't want to spend too much time on this. And this is the first work that we did with my PhD student, Yonggu Choi. That's how it started the structural compression as long as I see. And this is the first algorithm that achieves it. So here what we'll do. Here's the graph that I want to compress. I want to compress structure, so I don't know levels, but I need to put levels to explain it. Let me start from the first node. Okay, so what I do, this is the tree that explained what happened, but actually the compression string is here. So I start from node I randomly, and I store in string B1 the number of neighbors, not who is the neighbor, but the number of neighbors. In this case, 1, 2, 3, 4. This is the first what I store here. Okay, the number of neighbors in binary. And you can see this is my all nodes. I split the nodes into neighbors, F, D, G, J, and non-neighbors. And I delete all edges, one, this, and this. And I have a smaller graph. And then I choose one of the neighbors, in this case, F. And in this deleted graph, I do the same. I store number of neighbors of non-neighbors. That's what I continue doing it and adding here. This is basically the same except, and these are the nodes denoted by squares. When I delete a lot, some of the nodes are isolated nodes. And these isolated nodes will have only one neighbor. So it will basically one edge. It's important that the statistics of B2 is the same as the statistic of the graph, and this allows me to actually compute it, because what I need in order to prove that this is a good algorithm, I need to do this following. So let me finish the algorithm, I concatenate these two strings, apply, let's say, arithmetic encoding, and I claim that if you do this, the length of this algorithm is n choose to hp minus n log n, which matches the first two terms. The last term has the same order, but not the same. That's the fluctuating function again. Chapter 8 in the book or the original paper is, so you can see the analysis is quite complicated, but this is an example of an algorithm, an example of this information efficient computation when I know what learnable information there, what is the bottom line. And I've been algorithm that shifted. This is basically the philosophy of universal source coding starting from Shannon. Let's not focus on this. Let's move to the next one because it's more interesting. So now I want to move to preferential attachment. First, it can be proof that every permutation in an admissible set is equally likely. So the formula that I gave you before for entropy of a graph and structure works. And I need to understand gamma and an automorphism. So let's start with automorphism because it is interesting. When m is equal to 1, the preferential attachment graph is basically a tree. And you can see the number of automorphisms grows almost linearly. And we can prove it. When m is equal to 4, there is very little automorphism. The question is, what happens when m is equal to 2? So here what we can see. Okay, when m is equal to 2, so when m is equal to 1, there is a lot of part of the graph like this, or a tree, and basically this is the whole graph. So this node, when I permute, and there are many of them about ON, there is a lot of symmetry. In the m equal to 2 structure like this, when I permute them, give me symmetry. So what we first prove, okay, we first prove that for m equal 1 and for m equal 1 with probability 1, the graph is symmetric. Was for m equal 2 with positive probability small, it's still symmetric. And recently with Professor Wojciech from Poland and Dr. Magner, we proved that for when m is greater or equal than 3, the graph is asymmetric. And this is actually complicated proof. You can find in the book or the original paper. So there is little, for m greater or equal than 3, there is little symmetry. Now, in order to get my bottom line, I need to tell you what is expected regular log gamma. It is n log n, so it's almost like n factorial, except that this is no on, but on log n. So we know more or less what you expect. So what I will show you next, two things. I will show you how the entropy of the graph, level graph and structure graph, and then I show you an algorithm. Okay, so first, it was not clear to us what is the entropy of a graph, but the first term is quite easy to understand. Look, I have n nodes. These n nodes have neighbors. Every neighbor I need about log n bits. And every time a new node arrives, I have m connections. So this part is easy to understand. What was harder to do is the second part, and it was growth like n, and Abram and Wojciech and I did it in our paper. So this is important, that part, m times n log n. What about structural entropy? It was a little harder. And what is different here is we have n log n unexpected, but not m minus 1. So here the goal. Find an algorithm that for a graph constructed by preferential attachment with fixed m achieves this entropy. So that way optimal. Okay. And what I will show you next. But I'm losing my voice. So any question? Okay, this is the algorithm that Dr. Magne came out, and it is a beautiful algorithm. So this is the graph that I originally showed it to you. These are the nodes. The first thing I have to discover is directed acyclic graph from this one. It can be done using pilling algorithms, which I need to describe you later, but briefly, it is like this. I look for nodes of the lowest degree, find them, delete them. Then I find nodes of the lowest degree, find them, delete the edges, and so on. And from this, I can construct directly acyclic graph, which is this. You see, these are basically, so I have right now directed graph. And let me go back here. So the labels will be labeled by DFS and nodes, the numbers, plus backtracking number. There will be two numbers that I will store. So I will store it. So this is my directed graph. Let's see what is next. Okay, so here what we do. Let's start with node number 1. I start from here. I go through this edge to 2. And what I will store neighbors coming from the others 2. So m is equals 3. So I will store 2 numbers, 1, 1. I go here. Then I go to 3. I can't go anywhere. So I have to backtrack 1 back. And I will store also the other 2 connections, so 2 and 4. I go to 2, then I go to 4, 5, 6, 7, backtrack 2, 8, 8, where I go next, 8, 9, wherever 9 is, here, and so on. So I will be storing for every node, m-1 numbers, 2 numbers to which the outgoing wedge is pointed out, plus backtrack number. Okay, so here what we will do. Based on the vector number 1, 1, 2, and so on, I store empirical distribution. There are 7 backtrack number equals 0, 3, 2, 1, 3, 1, 1, 2, and so on. And I use constructed by Hoffman or arithmetic coding to do it. Then I store, this is important, for each visited node, single 2, and called destination of the outgoing edges besides predecessor. So look, from 1 I go through here to 2. So I'm not storing this, but I'm storing what are the other 2 nodes. The same here, I came through this and I stored 2 and 4. Okay, that's it. Okay, so I start from here. You see, I told you I store 1, 1, and there is 0 backtracking number. Then I go to 3 and I'm storing 2 and 4, but there is backtracking number 1, and so on. I continue this, and okay, so what's happened? What I need, how long is this string? I have for every node, I store m-1 destination, which calls me log n. So I have m-1 log n times n, plus I have to store a backtracking number, and this is actually a little complicated because I use empirical distribution. I can bound it by entropy, which I can bound it by log the maximum of backtracking number, which is bounded by the height of the dot. And actually, it is quite interesting and relatively simple, but not trivial to estimate that the height of the dot is log n. So because it's the log of log, I'm getting that my algorithm cost me m-1 n log n plus O n log n, which is optimal up to the first 2 terms. Okay. Okay, before I go, any further questions? We probably will need another 15, 20 minutes. Any questions so far? Okay, I probably lost you guys. So let's go back to the original problem that I wanted to do, which means I generate a graph according to preferential attachment on duplication node. I get a snapshot of the graph, and I want to recover the way the nodes arrive. I want to do inverse engineering and to reconstruct the graph. I told you that doing it exactly is impossible. So we're going to change the strategy. We're going to do partial order. So here what I do, I will basically, let's see, yes. I will basically, instead of recovering exact nodes, I will put them in bins. I can't tell you whether 1 arrived before 2 or 2 before 1, but I know that 1 and 2 arrived before 4 and 3, and so on. So I want partial. Of course, you have to be doing this in a reasonable way. If I have 1 bin, that is nothing interesting. I want to have as many bins as possible that with high probability I can recover. That is my job. Okay, let me show you an example. So this is my graph. This is the permutation that I got. I want to recover partial order. I want only to decide whether 4 here arrive before 1 and before 2. I'm not going to tell you anything about 3. What does it mean? That actually recovering much less information. Although 4 choose 2 pairs, I only tell you about 3 pairs. This is called density. I want density to be as close to 1 as possible. There is this permutation, 4 and 1 is good because 4 really, 3 arrive before 4. So in this permutation, out of 3 possible pairs, 4, 1, 4, 2, 1, 2, only 4, 1 is correct. So I recover 1 out of 3. This is called precision. Okay, and this is a formal definition. Okay, I want precision to be as high as possible. I want to recover as many correctly pairs out of all possible pairs that my partial permutation has. And I want density to be as high as possible. I want to have as many bins as possible, if you want to say this, and as few nodes in each bin. Now, what is the relation between precision and density? Okay, so this is something that we spend a lot of time, and computation is not trivial. I want to formulate an optimization problem. I want to maximize precision, subject to have density as high as I want, and then let's say epsilon. So here what we do, this will be a linear programming. At the end, I define a variable xuv, and that is 1 if u is arriving before v and 0 otherwise. And I want to maximize precision, which is basically PUV is probability of correct order between u and v for each graph. And that is basically what we had. This is basically this. Okay. So now there are subjects too, and the main constraint is this one, that I have a good density. Some other constraints are important. I'm not going to go through this. The main problem is how to compute PUV. PUV is basically probability that you arrive between V for a given graph H, and we can prove it. Actually, you can compute it using a ratio of all permutation which satisfies some criteria to all other feasible permutation. And actually, this problem is equivalent to counting the linear extension of partial orders. That is a complicated problem. What we did actually to compute PUV, use Markov chain algorithm, okay, Monte Carlo algorithm, basically. And what we got that the optimal curve between density and between permutation density looks like that. Why I need it? Again, for the same philosophy that I told you before. First, I know what is my bottom line. What is learnable information? once I know it, I can try to design algorithms that achieve it. And this blue part are this, but let me do it. Okay, so I'm gonna go here. Here's my peeling algorithm. This is my original graph. I look for nodes of the lowest degree, in this case, degrees 3 are 6, 12, 11, and 10. I delete these nodes. Then I'm looking for the nodes of the lowest degree, 9, 8, and 7, and so on and so on. I'm getting a dark. I claim these are the oldest nodes, these are the youngest nodes. So this is what is my algorithm. And the density is pretty good. So how this algorithm works against the optimal curve. So for artificial data, that is basically peeling algorithm, which is pretty good. There are some other that we can improve. So for artificial data, it works pretty good. And okay, one thing that I want to tell you, let me see. What we can prove is that if I have a pair like 6 and 2, when they are one is descendant than the others, or 8 and 5, I know for sure that these are correct order. It means this is younger than this, for sure. But I can't tell you anything between 6 and 12. So how many actually pairs? So remember, I have to choose n choose 2, n square pairs. So how many descendants I have here? It turns out that not that many. So let me go right now and tell you. So the perfect pair is the one that, this is the definition, and this is basically equivalent to a pair that you have, that is U and V is on the path in this graph that I show you. How many such a perfect pair? We only can prove it between n log n and n squared, O n squared. But actually, experimentally, and we have the conjecture that the number of this pair is 1 plus a small constant, not 2, that's what and it's not 1, so it's not n squared as we would like to have, but it's close. It's pretty good algorithm. Now, let me show you one possible application. Before that, here are some examples for synthetic data that we generated. Works pretty good. This algorithm will go so when M is not fixed but random. And this is called Cooper-Freeze model. These are another real networks when you can see that precision and density are pretty good, pretty high. But here's what I want to focus. So we got somehow data for a healthy brain of a young man, I think young man, and we are trying to see whether we can apply our pure algorithm to detect, to guess evolution of the brain. So here what we did, we got the data, we identified 46 nodes. The nodes is different function, walking, thinking, breathing, and so on. We connected 2 nodes. If the Pearson coefficient from fMI data is greater than 0.8, and we created a graph. I show you on one earlier slides, and we applied our algorithm. So these are the bin number 0, oldest part. These are the youngest part, and that's what we got. And anecdotally, we do quite well because there are some like corpus callosum, which everybody knows is one of the oldest parts, and there are some of the youngest like this one. The problem is how to verify it. We do not know the ground truth here. So the verification is a little harder. So here what we did, we bought data of 400 or 300 healthy brains for man, and we apply our algorithm to one particular region, let's say auditory region or visual region, let's say this one. We apply our algorithm 300 times, whatever, and we can see whether our algorithms return consistently the same ranking. So we want here a peak like this. That is pretty good, that is so-so. It looks like it is not bad. What we can say, it could be used as a original or initial filter to tell which part basically you need more detailed biological data, but they can give biologists or neurologists actually some idea what's going on. So this is one application. Okay, any question? I have only 2-3 more slides. Okay, so I introduced to Dr. Turotsky talk, which will be in 2-3 weeks, when he will be talking about duplication diversion network. First of all, here I plotted symmetry, P versus R. There are 2 parameters. You can see the bluer it is, the more symmetry it is. These graphs are symmetric. They have a lot of symmetry. And actually, we have experimental data, which I will not show you today, that biological networks have a lot of symmetry. Log of the automorphism is like 300-400, log of the automorphism, a lot of symmetry. We still don't have a proof, theoretical proof of it. We have experimental proof. So first of all, our algorithm compression that we have from preferential attachment wouldn't work. Second, it's not anymore true that every permutation with the admissible graphs are equally likely. So our expression for the structural and graph entropy is not anymore applicable. We need something else. So, well, again, Dr. Turotsky tells you more. Basically, we try to apply the same philosophy for the protein-protein network, which falls under the duplication graph network. And this is much, much harder problem. We couldn't estimate PUV. And here is basically our algorithm that shows the optimal curve, which was experimentally contained, and our prediction whether the density versus precision. I'm not gonna go into this too much because we will have probably some more discussion in 2-3 weeks. Let me conclude. So at least in dynamic networks, which are an example of a complex system time evolving, there are many interesting problems. The first one is to understand what model generate the graph. And that is actually very important. We have one simple paper with Dr. Magner in RT. So here it is. You collect data from dynamic graph, let's say brain network, and now you're trying to say what model, preferential attachment, duplication, or something else generated. So like from a histogram, kind of, you are trying to understand what the distribution, what the model generates. Much harder problem at basically getting non-stationary Markov. And good luck with this. Second, infer spatial temporal property that I show you. For preferential attachment works quite well, for duplication not very well. And the last number is probably minimum bits, so the compression. There are many more work. Venkadanatharam, professor from Berkeley, generalized it to universal, very general graph. You can see it. You can see it. And the other thing is prediction. So let's say you see evolution up to now. What can you say how the evolution will look in 100 of years? So this is another thing that could be done. But there's a lot of work there that is still not done. So this is Acknowledgement. This is my co-author, Professor Grama from Purdue. Abraham Magner, he's right now in Alabama. Jisin, he was a postdoc here. He's right now back in India. I think he's working for a company, and Dr. Turotsky is with you. I think that's it. Yeah. Okay. Any question? I see most of you are still there, which is good. As I say, we probably will do it for 1 hour, and as long as there is a question, there is a question, Pan Maciej. Proszę bardzo, please go ahead.
Yes, I have one question because, can you hear me?
Repeat again.
Yes, can you hear you?
Can hear you, Maciej.
I'm not
Okay,
sure.
and can you hear me now?
Yeah, I can hear you, but yeah,
Okay.
go ahead.
So my question is, because you described to us that you had some data about structure of human brain, and you ran it in an algorithm, and you received some division or distribution in something like brackets. But do you have any interpretation of why each part of brain ended up in each bracket?
So part of the brain of what bracket? What is bracket? I'm not sure I understand the question. I hear you, but I don't understand the question.
Okay, so maybe I didn't understand. From what I understand is that you had parts of brain,
Yes.
and each of them ended up in a bracket, or
so so we had a linear partial order. We put in the bins, or basically saying that certain. So it's quite possible that certain area in the brain will develop at the same time. Yes. So it makes sense, instead of classifying or trying to get linear order of each part of the brain, you basically put them into this bin. That's what we did. Verification is a different story. I'm not sure I'm answering your question, but that's all what I can say about it.
okay, so maybe now my question will be more understandable. I guess it's about why each part of brain ended up in each bin, so why some parts of the brain were developed earlier. But from what I understand, you
So
don't.
by the way, here is, by the way, one thing that I should say, and you probably pointed it out, the question that you want to ask, why we apply preferential attachment model, the model that generates that is used in evolution. That is a hard question. We don't know. That's why one of the problems that with Dr. Magner we try to analyze it is the following. Okay, if I have this data from the brain, how this, let's say from fMRI and so on, how this graph was generated, can we confirm with high probability that a good approximation of the graph generation preferential attachment? No, we don't have this. We have some preliminary results. Do you understand what I'm trying to say? That what is hypothesis testing on graph? Do you understand what I'm saying?
Yes, I do.
Okay, so this is a very interesting problem. And again, one paper that we have is ILT 2020, I think. You might want to look at it. With real data, the same protein-protein network, we don't know the grand truth. In protein-protein network, there are a little better work done by physiological tree, and they actually can better linearate, better give us better understanding of aging of protein network. In the brain, it's much harder, as I understand, but I'm not expert in this. So it was an application. Anybody else? Okay, so what we do next week, I will talk about something very different. For last year, I worked with one guy in Google, Gil Shamir, and we work on actually online regression, an algorithm there, and regret. So it's more theoretical and more closer to my heart because I did a lot of work on regret for information theory. So this will be actually a review. I gave a talk in Google, how they call it, Let's Talk Tech or something like this. And there will be 3-4 different problems related to online and supervised, non-supervised learning, but mostly online learning, and trying to understand how regrets behave, plus an algorithm that actually we believe achieves this lower bound, but we cannot prove it yet. So that's what I plan next time. Anything else? Any question? Now, again, if you have any question and complaints, do it. Talk to Dr. Turowski, okay? You can complain to him. Yes, Krzysztof?
Yeah, and you can complain to me too.
Okay, guys, thank you very much. Have a nice day.
Thank you. Have a good day.